In video 46 of the Foundations of Computational Economics, we will be talking about the nested fixed point estimator, which is the member of the family of maximum likelihood estimators and is a classical estimator for the dynamic discrete choice models. Together with the method of simulated moments, it's one of the most popular methods which are used in the structural econometrics to estimate dynamic models. Now, not all models can be estimated with maximum likelihood estimator. We must require that the model yields some probability distribution for the observable data. So essentially, having a certain model in mind, which depends on the parameters, we can write a PDF, which I denote L here, some distribution. We can describe some distribution of the observed variables x, conditional on on some values of parameters. And then we can couple this PDF, which is defined by the model, with the, say, a random sample of n observations in the data in order to arrive at the estimates for theta. So in the case when L is a discrete distribution, we can just plug in the data in place of x to get the probability of observing those variables, those values. So, rolling a dice has a probability of 1/6 of having any particular number, and so when you observe those numbers, you can invoke, sort of plugging in requires invoking this probability is 1/6. If you observe 3 is rolled, that means that you can directly calculate the probability of getting that 3 from the distribution that the dice itself yields, essentially, right? So the dice as a model gives you the distribution of the outcomes. Now, if L of x and theta is the continuous distribution, then calculating the PDF at the observations is somewhat different, but it is analogous to the probability of observing a given point in the data. In any case, irrespective of the nature of the distribution, we form the likelihood function just like this, right? Assuming that the observations are independent, we can take the product of the probabilities of each observation zi. And this likelihood function, which depends on n observations, essentially corresponds to the likelihood, the chance of observing that particular sample. And this is what we want to maximize with respect to theta. That's the definition of the MLE estimator, maximum likelihood estimator. It's the argmax, so the value of theta that maximizes the likelihood function, essentially, right? And here I'm introducing new notation. This L of zi is going to be the likelihood of a particular observation, and the subscript n is denoting the likelihood of the whole sample of ID observations, and n of them. Anyway, it turns out that it makes a lot more sense to work with the log likelihood rather than the likelihood itself. So by taking the logs, we can convert this product into a sum of the logs of the likelihoods, and the corresponding notation here is going to be the small curly L that we will work with everywhere. And of course, the estimator doesn't change. This transition is possible because log itself is in a monotone function. So we are making a monotone transformation, and that doesn't change where the maximum is attained. All right, so straight to the asymptotic properties of the maximum likelihood estimator, just listing them here. The estimator is consistent, which means that it converges in probability to the true value, denoted theta naught everywhere. The estimator is asymptotically normal, which means that we converge in distribution to the normal distribution with a particular variance-covariance matrix that we talked about in the moment. I'm sorry. And this convergence is in distribution as the number of observations increases. MLE is asymptotically efficient, and this is probably the main property to remember about the maximum likelihood estimation. MLE approaches and reaches actually the smallest possible variance of the unbiased estimator. You cannot achieve or obtain any smaller variance of the estimators than the what is possible with MLE. MLE also has this functional invariance property, which means that if you want the maximum likelihood estimator of a function of the true parameter or true value of the parameter, then you can calculate this as a function of the estimator, well, under certain irregularity conditions. Okay, we are mainly concerned with the asymptotic variance of the MLE estimator and how to compute it. And here is a brief summary of how it's done. It's quite fascinating. So the fact that this expression converges to the normal distribution is equivalent to being able to calculate the variance from what's called the Fisher information. This curly I notation here. And by definition, the Fisher information is the variance of the score function computed at the true parameter theta naught, where the score is simply the derivative of the log likelihood. And I'm skipping a lot of derivations here. You can show that this Fisher information is equal to these two, or can be given by these two equivalent forms. It's either the negative expectation of the second derivative of the log likelihood, or it is the expectation of the square of the derivative of the log likelihood function. And here we're thinking of this Fisher information as just calculated from the distribution induced by the model, right? Without the random sample. But it's also possible to talk about Fisher information with a subscript n here, which basically refers to the same thing calculated for the likelihood function of n independent of observations. And you can show that this is, there is simple relationship here. This is a point which is a little bit confusing in some textbooks, and including the Ada and Cooper book that we have on this syllabus. Now, Fisher information is hard to compute. Why is that? Well, because in our case it depends on the distribution which is subject to the model, right? That's induced by the model, and we can simulate from this distribution, doing simulations from the model, but we don't have an analytical form of the PDF that the model implies. But on the other hand, we have a nice consistent estimator due to the law of large numbers, which is basically, taking the average of the second derivatives of the log likelihood function. You can you have this result that it's not that hard to derive actually this convergence in probability to the Fisher information. And then we can write what's sometimes referred to as observed Fisher information, which is the average of the second derivative of the log likelihood calculated at different points of the data. Right, and this is the estimate of the Fisher information corresponding to the no, sorry, I'm sorry. So this is the estimate for the one observation Fisher information, and then multiplying that with n gets rid of this 1 over n in this formula, and this corresponds to the Fisher information of the n independent observations. All right, we still can't calculate this because this depends on the true value of the parameter, and here we take the standard step of plugging in the estimate itself into the formula, and we get something like this, which roughly equals, not completely precisely, leads to the estimate, which is the MLE estimate in this case, being distributed normally, centered around the true value of the parameter, and having the variance covariance matrix given by the inverse of this observed Fisher information. Okay, that's the end goal. We want to be able to calculate the standard errors of our estimates, and the standard errors are going to be, on the diagonal of this matrix. You also have to remember to take the square root. But we have to continue talking a little bit more about this, because this also has to do with how we calculate this observed Fisher information. We don't really want to calculate the second order derivative, although we might do that if really needed. But here's a beautiful fact. Remember I said that Fisher information itself can be given in two equivalent forms, and this one only requires the first derivative of the log likelihood. And it turns out that a similar expression holds for the observed Fisher information, and in fact this is correctly written for theta naught being a scalar. Now if we have a vector of parameters, then things are a little bit different. We need to adjust both sides of this equality here, and the first adjustment is to just realize that the second derivative will now become the Hessian matrix, so it's going to be a matrix of k by k elements. But what to do with the square of the gradient? That's not completely straightforward, but we may have to go back a couple of steps in the derivation of this equality, and I can tell you that it originates in the calculation of the variance of the scores of the first derivatives of the log likelihood function. And as many of you know, the variance can be expressed as the difference between the expectation of the square of the random variable and the square of the expectation. Well, the expectation of the first derivative of the log likelihood for MLE, and particularly at the true value of the parameter, assuming that the model is correctly specified, is 0, right? So this term here, which became this term here, it relates to the variance of the first derivative of log likelihood. Well, how do we do variance if we have a vector of random variables? We have to think of the outer product operation. So consider a vector of random variables, say k random variables, so that they form a column vector k by 1. Okay, we can calculate the expectation in a straightforward way and get the same dimensions of the vector of expectations. But then, in order to compute the variance, what we usually do is we find the variance covariance matrix, and it is given by the expectation of what's called the outer product of the vectors. So instead of multiplying vectors in the usual dot product way, to get just a scalar, we kind of rearrange the vectors so that the column comes first and the row comes second, and what we get is the big square matrix where each element is just the product of two things. Right, this one forms the first, and this one forms the second, and so forth. And so the same thing happens here, except now we have to take the outer product of the centered random variables here. So we subtract the expectation. And then, of course, the variances lie on the diagonal of this matrix sigma. And off diagonal, what we have are covariances between the elements of the vector. All right, so a similar thing happens in our observed Fisher information. And here it's handy to introduce some new notation. So first, let's realize that the second order derivative of the log likelihood function forms the Hessian matrix of the log likelihood function on the whole sample, right? So this is k by k Hessian matrix. Now, if we take just the first derivative, then what we get is a gradient, and denoted with this nabla symbol here. And this is going to be a k by 1 vector. But we can also remind ourselves that this ln is actually, if I go back to the very beginning, this small ln is the sum of the individual contributions to the log likelihood. And so, where were we? We were here. And so, let's take the first derivative of each of these individual likelihood contributions. It's going to be a vector in each of these cases, right? If theta is a vector. And then we can stack those vectors to form the matrix of k by n, where n is the number of observations and k is the number of parameters in theta. And I'm going to denote that with this symbol, with nabla L of the whole data. And again, this is going to be k by n matrix. Well, it turns out that the second component in this equivalence here, it requires us to do the outer product of these matrices, or what is that is equivalent a sum of outer products of the derivatives of this log likelihoods calculated at each observation. And here we have just the Hessian matrix. All right, and this whole expression, you know, the fact that the Hessian matrix is equal to the outer product of the gradient is called the information matrix equality. So let's summarize and conclude. You know, this is going to be what is to be put into code. The maximum likelihood estimator is given by the argmax of the likelihood function, which is calculated from the individual contributions denoted here, small l of each data point, right? Log likelihood. And we can maximize log likelihood, all likelihoods. This is a bit easier. Theta comes from some parameter space, and we have an observed data, which is a random sample of n observations. Now we have this result here, which is somewhat sloppy notation, but this is what's practical. The estimator, the maximum likelihood estimator, is distributed, approximately distributed as normal, centered around the true value, and has the variance covariance matrix given by the inverse of the observed Fisher information, where the Fisher information is, well, it's equal to the negative Hessian, but it also is equal to the outer product of the gradients of the log likelihood function computed at each observation. And you can see here that, you know, we can use the first order derivative only, and compute it at each of the observations to be able to calculate the standard errors. And this is pretty nice. You know, taking just one derivative is always better than taking two. But moreover, This equivalence, the information matrix equality, leads to a wonderful optimization method, which is referred to as Berndt-Hall-Hausman algorithm, BHHH. So we take from the information equality the fact that the Hessian asymptotically, right, as n approaches infinity, is equal to the outer product of the gradients computed at each observation in the data. And remember, the Hessian is something that we do need to calculate for the Newton optimization method. And the whole family of methods called quasi-Newton rely on some sort of approximation of the Hessian matrix. Well, and here we have a formula for approximating Hessian at any point theta, based on the fact that a true value of theta at the true value of theta, we have this exact equality. Right. Great. So we can form our quasi-Newton optimization algorithm based on this approximation. That allows us to only use the gradient of the log likelihood function to understand something about the shape, the Hessian of this function. Moreover, the outer product of gradients results in a semi-definite matrix. We have a minus here, so it's a little bit risky to say whether it's positive or negative semi-definite, but I can tell you that the Hessian approximated with BHHH will always point in the right direction to the increase of the likelihood function. And because we approximate in the Hessian, and also to ensure a global convergence of the method, it's usually included into the algorithm the search for the appropriate step size. So, the Hessian tells us in which direction to make the step, but the size of the step can be refined additionally by looking or by ensuring that we always walk into the direction of the increase of the functional value. Also, here is the BHHH reference in the literature. This is a really beautiful algorithm. It works very reliably. It's almost as fast as Newton method itself, it just gets you to the top of the likelihood, at least to the local optimum. Unfortunately, it's not general, right? Because it is developed and is applicable for the maximization of the likelihood function. But if you are maximizing likelihood, this is what you should use. All right, back to the bus engine replacement model. This is the model in the course which admits the maximum likelihood estimator. And as I was saying in previous videos, namely 28, 29, and 44, John's paper, Econometrica 1987, was a very significant contribution on many levels. It is a complete package in both how to solve the model efficiently and how to estimate it efficiently. And the NFXP algorithm, the nested fixed point estimator, was a natural part of this whole package of this paper. But we are looking at it separately only now. So let's remind ourselves about the main equations in the model. We have the value function with two variables in the state space, the mileage, which is discretized into bins, and this continuous vector of IID extreme value type 1 shocks, which we will be integrating out, but which will give rise to the choice probabilities of the logit type. This is a very nice structural way to account for the discrepancy between the predictions of the theoretical model and the observed data. And so we are, by including this unobserved state variables, we are allowing or we are avoiding the degenerate distribution that this model would yield. Instead, it you know, with the taste shocks included into the structure of the model like that, this is what allows the model to actually make predictions on the distributions of the observed data, and therefore admit the estimation with maximum likelihood. All right, so as you remember, we converted this Bellman equation into the fixed point equation for the for the expected values, the EVs. In theory, they are written as a function of states and decisions, but in the implementation in the code, we can skip the argument of the decision, because the first value, the value that corresponds to x equals 0, is actually fully describes the expected value of replacing the engine. So in the code implementation, EV is just a single vector with a number of elements equal to the number of grid points on x. So it's like the EV of x. But in any case, we have this fixed point equation in the expected value function space, and also, as you would remember from video 44, we can represent this equation using matrix multiplication or matrix algebra. The sum of some components weighted by the transition probability pi can be written as a multiplication with the transition probability on the left, for example. The instantaneous utility in the model is given by this utility function or cost function. We want to maximize the negative cost, and here I want to emphasize that there are some parameters. So in fact, one parameter, theta 1, is a scalar parameter in the cost function, and there is this parameter, the replacement cost, which is also something that we need to recover in the structural estimation. The transition matrix for the mileage includes 3 parameters like that, and they are repeated in the band diagonal fashion because the buses cannot drive too far, right? So there are a lot of zeros for the new bus in one time period. And now here's finally, it's going to be obvious what these choice probabilities are used for. The expression for the choice probabilities is this, or we can simplify it a little, or convert it into this simpler expression. But the point is that they depend on the instantaneous payoffs of all of the options that the decision maker has, 2 in this case, and they also depend on the expected values of taking each decision. And here, in the short notation, we just keep in mind that everything depends on the structural parameters theta, but in the estimation, we will actually add little subscripts to emphasize that. So where are we so far? What have we done so far? We have the machinery which can, for every value of structural parameter theta, this whole vector here. Oh, there's a typo. Typo is here. Should look like this. So for each value of the structural parameter theta, we can solve the model using the combination of Newton-Kantorovich and successive approximations in the Pauli algorithm, which is really robust. And based on this solution, here's my subscript theta here, we can calculate or form the choice probabilities, the probabilities to keep and replace the engine. And these probabilities, this choice probability, is exactly the distribution that the model is required to yield in order to perform maximum likelihood estimation. Because think about this. Now imagine that if we have data on mileage on axis and the choice is D, we can plug these observations into the choice probabilities and therefore calculate the probability of observing each of the data points. Right? So having the choice probabilities allow us to form the likelihood function and proceed with maximum likelihood estimation. Well, let's think about the data first. In the original paper, Harold Zerker is the superintendent in this bus company, and he maintains the records for 162 buses, which are divided into 8 groups. And there are monthly observations on mileage of each bus, which are then discretized into the bins, and data on maintenance operations. Was it a routine periodic maintenance, like brake adjustment? Was it a replacement or repair at the time of failure? Or was it a major overhaul and replacement of the engine? We disregard this breakdowns, and we want to record whether the engine was kept and the bus was just casually maintained, or whether there was an overhaul or replacement of the engine. So in fact, we are observing X's and D's in different time periods in each month T for each of the 162 buses indexed I. So this is the data which we exactly need to be able to proceed with maximum likelihood estimation of the bus engine replacement model. So let's form the likelihood. Without the logs, the likelihood for the whole sample looks like this. Right? We take the products of the choice probability coupled up with the transition probability in each of the time periods where this is defined. And converting this likelihood into logs gives us the nice sum, and the probabilities of maintenance, of transitions and choices, according to the conditional independence assumptions, they separate into 2 different probabilities. And because we know that some parameters enter one part and the other part, and other parameters enter the other part, we can actually estimate them separately, at least first, before going to the joint estimation. I'm not going to be talking about this, but John's paper details this approach as well. So again, the maximum likelihood estimator is given by the argmax of this function. But now observe that the likelihood function also implicitly depends on the expected values which form the fixed point, the solution of the model itself. And that's because these choice probabilities depend on the equilibrium or on the solution EVs. Right? This is an essential part of estimating dynamic models. So likelihood is now, or can be written not as a function of theta itself, but also as a function of the expected value, which constitute the fixed point, and everything there in the solution of the model also depends on theta. So this gives rise to this nested loop approach. We can maximize likelihood on what can be referred to as outer loop. This is the hill climbing algorithm that is searching for the maximum of the likelihood. But each log likelihood function or each evaluation of the log likelihood function requires the solution of the fixed point problem. And this is what's happening on the inner loop, the fixed point algorithm. And therefore two nested loops and nested fixed point algorithm. So the inner loop solves the model for the fixed point of the Bellman operator gamma, conditional on theta. Here it's important actually to add subscript theta to the gamma operator as well, because it's the gamma operator takes the expected value functions and transform them into another expected value functions. But because it, for example, the gamma operator itself depends on the utility, then gamma is also indexed or parameterized by by theta itself. And so the inner loop performs the Pauli algorithm to solve the model, to find the fixed point, and then gives it back to the likelihood function. And likelihood function can be estimated, calculated, and then given back to the quasi-Newton algorithm based on BHHH, of course, to take the next step in the direction of the higher likelihood. And in order to evaluate this likelihood in the next point, in the new point, we have to solve the problem all over again. And therefore, in order to estimate the model and find the theta, the values of the parameters which maximize the likelihood, we have to solve the model very many times, many times. And that's why we were so concerned with the efficient methods of solving the model, right? Because the solution is nested in some other loop. And, as I mentioned, this paper and this model gave rise to a larger literature, and nowadays you may have another loop on top of this whole two loops that, for example, calculates the equilibrium, or maybe there's an intermediate loop that calculates the equilibrium of the model before it can be given back to the likelihood. So this need for a more efficient algorithm is never ending. Okay, some important details, some of which I've already noticed. Performance-wise, we really want to employ the gradient-based Newton-type maximizer for the likelihood. This is imperative because that's so much. It's hard to calculate each evaluation of the likelihood. So we want to minimize the number of these evaluations by employing an efficient algorithm for the maximization itself. To do that, we need analytical gradients, right? The analytical gradients means that we can write down some formulas on a piece of paper in order to have a precise set of instructions to calculate the gradient of the likelihood function without having to solve any equations numerically or doing any other iterations numerically. It should be all in one go, like EGM method. And it turns out to be possible to write this analytical gradients for the likelihood, but it requires the use of implicit function theorem and lots of applications of chain rules. And it also turns out that the Fréchet derivative through the sum of the chain rules is going to be really useful. The Fréchet derivative of the Bellman operator is going to be really useful in calculating the derivative of the likelihood function itself. And this is also where we wanted to avoid the calculation of the second derivative of the likelihood function, because it would require some second-order Fréchet derivatives of the operators and things like that. So it's just it's nice to be able to avoid. Then we're using BHHH in this application, as everybody should when maximizing likelihood. For numerical stability, there are some issues that may make the whole procedure unstable, and primarily it has to do with calculating log sums in the right way with recentering or demaxing, and same thing for choice probabilities. So every time we're calculating the log, we should ensure that we're not plugging or calling that for a zero or a negative number, and every time we're calculating the exponent, we have to make sure that the number cannot get too large. And all of these details are laid out in what's called the NFXP manual, an unpublished document available from John's website and also through the repository with these lectures in the static PDF folder. Now, just a couple of words on the analytical gradient of the likelihood function. So this is what we need to calculate, right? The derivative of the likelihood function with respect to the structural parameter theta. This is going to be needed for applying the BHHH algorithm. The differentiation carries through into the components. So the derivative of the transition probability, which is basically parameters themselves, is pretty obvious. And in the differentiation of the choice probabilities, which have this complicated form, we will need to apply chain rule many times. but it all comes down to the derivatives of the utility function and the derivatives of the expected value functions. And this is where the only issue that arises with this differentiation is. In order to get the derivative of the expected value function, which constitute the fixed point, right? It's not that straightforward. We need to differentiate something that depends on the parameter, but it depends in the implicit way by satisfying an equation. Well, there's a Banach space version of the implicit function theorem, and with all the necessary technical requirements satisfied, or assumed to be satisfied, we can apply this theorem to the fixed point equation of the model itself, also realizing that the gamma, the Bellman operator, is a function of theta just by itself. We have this expression here, and you can see that this can be solved for the for the derivative of the expected value with respect to structural parameter, which takes this form. And Frichet derivative shows up in here just as well, but because we had to calculate the Frichet derivative for all different values of EV in order to find the fixed point on the inner loop, then we can just pass it from the inner loop to the outer loop from the last iteration and use it here. And here we need to do one more inversion of the matrix and multiply it with this derivative of the Bellman operator with respect to the structural parameters. And this is also something that is very easy to imagine when we are working with finite approximations of the operator in the code. So this is going to be essentially a non-square matrix, the n by k matrix to represent this derivative. And so these are all matrix operations, and so we will calculate the again n by k matrix of the derivative of the expected value function that can be plugged back into the choice probabilities or derivatives of the choice probabilities, and essentially leads to the gradient of the likelihood function. So this is all of the theoretical background that is needed to write the code. Here's the pocket guide for the nested fixed point maximum likelihood algorithm that details both the side that is solving the model that we were looking at the previous several videos at. So it has to do with the Newton-Kantorovich iterations and successive approximations, contraction iterations, and switching between them to solve the model. And the outer hill climbing algorithm, which is the BHHH algorithm with additional search for the step size in the direction chosen by the approximated Hessian. And how this parts there's an error here. How these parts work together in the nested fixed point estimator. If you would like to keep all this knowledge with you, it's pretty easy to print this out and put into your pocket. Therefore, we need a pocket guide. Now we are ready to implement the NFXP estimator. And of course, all the background work is done in the Zerker class, where we have implemented the inner loop. But what's left to implement is the outer loop. So the likelihood function, the optimizer, the calculator for the standard errors of the estimates, and we also need the derivative of the Bellman operator with respect to the structural parameters. So this implementation comes next, but in addition, I can point to a very nice implementation which is already packaged and is available as a Raspberry package from Maximilian Blasch in the computational economics group at the University of Bonn, who are called Open Source Economics. Here are the links. to their work, which you're very welcome to check. Now, this is going to be the end of the first part of this video, and the implementation of the NFXP estimator in our code will come in the next part, but will not be the part of the exam for the course. That's the end of this video for now, and see you in the next one.